Let's get started. So if you recollect in yesterday's class, we were looking at the overall closed loop feedback control system. Today we will be looking at the PID controller. We identified that the overall control design problem involves working with the C of S, right? So we identified three what to say main transfer functions: the plant transfer function P of S, the feedback transfer function H of S, and the controller transfer function C of S. So the overall control design problem deals with figuring out the controller transfer function C of S to ensure closed loop system stability and performance. Okay, so in that regard, like the PID controller is a very popular controller. The full form for PID is proportional integral and derivative controller. So in today's class, let's look at the PID controller. Let's look at the structure of this PID controller, and also like what are the features of this, and how do we go forward with this, right? So if you look at the PID controller, the first block is P, which is the proportional controller. What happens is that the control input is directly proportional to the error E. So if you recollect, the controller is this block, right? Which essentially takes in the error signal and gives us the control input. Okay, so we should keep that in mind. So when we deal with the controller transfer function, so we are looking at C of S. The controller transfer function is C of S. The input to that is E of S. The output from that controller block is U of S. So that's why U of S becomes equal to C of S times E of S. Okay, so that's how we get that expression. So in proportional control, the control input is directly proportional to the error E. So the equation for U can be written as Kp times E of t. And if we take Laplace transform, we get U of S to be equal to Kp times E of S. Okay, so essentially that's what we have. So consequently, the controller transfer function, which is the ratio of U of S to E of S, right? Because anyway, the transfer function of any block is the ratio of the Laplace of the output to the Laplace of the input, right? Under zero initial conditions. So here the output is U of S, input is E of S, right? For the controller block. So that's why the controller transfer function is U of S by E of S, and that is Kp. Okay, so here we can see that the transfer function is very simple. Okay, just a scalar real number. Okay, because Kp is a real number, and it's called as a proportional gain. Okay, so because it's a controller parameter associated with the proportional controller. And see, if you look at the field of control systems, right? So there have been contributions from people from multiple engineering disciplines. The word gain is typically used by electrical engineers. Okay, so they talk about circuit gains and so on. Kp is the control gain. Okay, so where we want to essentially multiple Kp, and then we get the control input U of t. Okay, so Kp is what is called as a proportional gain. So since there's only one real parameter, right? The main advantage of the proportional control is its simplicity. Okay? So it is very simple in structure. So by and large, like one would try to start the control design with a proportional controller. Okay, so if a proportional controller works, it's well and good, right? So as we go later on in this course, we will observe that for certain classes of systems and under certain scenarios, the proportional controller can lead to non-zero steady state tracking errors. Okay, when tracking constant reference inputs. So what do I mean by that? Like let us say, we have a case where, let's say, we want to control the temperature of air in a room, and we set it at 25 degrees Celsius. Now, I'm just giving an example, okay? So let us say it belongs to some conditions are satisfied where the due to which the proportional controller will lead to non-zero steady state errors. So what it means is that like you and I may want 25 degrees Celsius, but the temperature may always settle down to 26 degrees Celsius. Okay, so that may be a issue with proportional control. Okay, so when we have only purely proportional control, not always, but in some cases. Okay, so we can have non-zero steady state tracking error. Okay, so that's what may happen with pure proportional control. Okay, so then what happens is that like what are the other choices available? Of course, one would typically start with proportional control. If it works, well and good, right? So if it doesn't work, we need to have alternatives, right? What are the alternatives? So we go to the other two blocks. Okay, so the next block is what is called as an integral controller. So as the name indicates, here we are going to deal with integral of error. Okay, so we observe that in the integral controller, the controller input is proportional to the integral of the error signal. So what we do is that like we integrate the error signal, let's say from 0 time to time t. So that is that integral 0 to t e tau d tau. And then we multiply that integral with a gain, what we call as an integral gain ki. Okay, so the integral gain ki is a real valued parameter which multiplies this integral. Okay, so and that gives us the control input u of t. So if we take the Laplace transform on both sides and then we calculate the control transfer function, now u of s divided by u of s comes out to be ki by s. Okay, so we can immediately observe that now we are no longer having a constant term, right, like in proportional control, but we have the s term coming into the picture, okay, in the controller transfer function. And since we know that the open loop transfer function is c of s times p of s times h of s, okay, so whatever be p of s and h of s, right, due to this. So, and as we know, the poles of the open loop transfer function are what are called open loop poles, and the zeros of the open loop transfer function are called open loop zeros, right? So, as soon as we use integral control, we see that we have a s term in the denominator of the open loop transfer function, and consequently, we introduce an open loop pole at 0. Okay, so we'll see what the consequences later on. Okay. So as we all know, in any design process, nothing comes free, right? There is always a trade-off between various attributes. So we shall observe that even using integral control has some, see what is the impact of having an open loop pole at the origin, when we use an integral controller. So what are the advantage of integral controllers? The main advantage is that it addresses the limitation of proportional controller. That is, it leads to zero steady state tracking error, right? When it can guarantee zero steady state tracking error while tracking constant reference input. So if we take the previous example, just for the sake of understanding, let's say we want 25 degrees Celsius as the room temperature. If you use integral control, it is going to go to 25 degrees Celsius asymptotically. Okay, so that is what do I mean by asymptotically? Asymptotically means as t tends to infinity. Okay, if you wait long enough, it will go to the desired value. Okay, so consequently, that's an advantage with integral controller. But what is the limitation? To understand the limitation, let's look at this plot. Okay, so if we look at this plot where we have plotted E of t versus t, we can observe that we are plotting the historical evolution of the error. Let's say the controller is working fine, the error is decreasing, which is what you and I want, right? See, ultimately, if a closed loop control system works well, we want the error to keep on reducing and ultimately go to 0 with time, right? So that's our expectation, which is happening here. However, let's say we take some time t and we integrate. What is integration graphically? It is calculating the area under the curve. So we observe that although the error may be decreasing, what can, let's say we keep t to the right, what happens? The area will,
It will increase, sir.
it will increase, right? So let's say
Right.
we are at T1, this is the area. Let's say we go to T2, although the error at T2 is lower than T1, there is an additional area which is added, right? So consequently, what can happen is that although the error is decreasing due to the fact that you and I are integrating the error, we will keep on increasing the control input, although the error is decreasing. And that's something which you actuator saturation. Okay. So actuator saturation is the phenomena where as we keep on decreasing the error, right? Although the error decreases due to the nature of the integral controller, the control input increases in magnitude, right? And it may go beyond the capacity of the actuator. Please remember, although U of t is output from the controller, as we discussed in one of the discussed classes, the control input has to be realized by an actuator. So what do I mean by that? Let us say we have a motion control application, right? So we want to move a platform or a linear motion stage, right? Let's say there is an electromechanical actuator which applies a force on a stage or a platform and moves it. And let us assume that the capacity of the actuator is some 100 Newton. Okay. That is the capacity of the actuator. Now, let us say at this instant of time, when I use an integral controller, I calculate the control input as integral of the error till now. Let's say the value comes to be 98 Newtons. I will be able to apply that 98 Newtons because it is below the or within the capacity of the actuator. The error decreases, but let's say the control input keeps on accumulating, and let us say the control input becomes 105 Newtons a few instants later. Now, the capacity of the electromechanical actuator is only 100 Newtons, but my controller is asking me to provide 105 Newtons. There is no way I can do that, right? Because I have gone beyond the capacity of the actuator. And that's where we will have an issue because you and I would have encountered actuator saturation, okay? Because we would have gone beyond the actuator's capacity and that cannot be realized in practice. This phenomena of actuator saturation is also called as integral wind-up. Okay, so integral wind-up, actuator saturation are all used to um, you know, refer to this phenomena, okay, where the control input, which is calculated by the actuator, by the controller, has exceeded the capacity of the actuator. Okay, so that's a limitation with integral controller, which you and I need to be aware of. Okay, now comes third part, which is the derivative controller. This is the D in PID. Okay, so once again, very intuitive, right? So as the name derivative indicates, here the control input is proportional to the time derivative of the error signal. Okay, so U of t is proportional to d dt, and we multiply. Any questions? No. So we multiply the derivative with the gain kd, the derivative gain, valued parameter. Okay, so now if we take the Laplace transform and calculate the controller transfer function, we get the controller transfer function of the derivative controller block as kd times s. Now, same thing, right? So if we take g of s h of s, which is c of s times p of s times h of s, If the controller transfer function is KD times S, right? Then what happens is that we introduce an open loop zero at the origin. Okay, so that's what happens with the derivative controller. And please note, the derivative controller as an individual block is not proper. Okay, so it is an improper transfer function. But ultimately, you and I want the open loop transfer function and closed loop transfer function as proper transfer functions. So I hope we recall what are proper transfer functions, right? When is a transfer function called as proper? No.
When the denominator power is more than the numerator power.
Exactly, right? So when the order of the denominator polynomial n is greater than or equal to the order of the numerator polynomial m. So if you look at the derivative controller KDS, then m will be 1, n is 0. So KDS as a standalone block is not proper. But the point is, that's why it's bringing an anticipative nature. Okay, so we will look at that shortly. We know that proper transfer functions are associated with causal systems, right? Causal systems are non-anticipative. So when we do not have a proper transfer function, that corresponds to an anticipative system, and that's what the derivative control is, right? So the derivative control anticipates what's going to happen, and then takes corrective action. Okay, so in order to intuitively understand that, once again, let's say we plot a graphic, right, involving the error versus time. Let's say without loss of generality, the error keeps on decreasing, right? Now, let us say at some time t, we want to calculate the derivative. So graphically, the derivative is going to be the slope of the curve. So now, at this point, what you and I can say is that, like, look, oh, okay, the slope of the curve is negative. That means in the near vicinity of time, the error is going to decrease. Okay. On the other hand, let us say at some point, the slope of the curve is positive. Then we know that the error is going to increase in the next instant of time. At some point, let's say the slope is 0. Okay. That means that the error is going to remain constant in the immediate the curve, right? You and I will be able to figure out what's going to happen in the immediate next instant of time as far as the error is concerned. And that is why the derivative controller brings certain anticipatory characteristics in the control response. And that is something which is desirable, right? So see, if a controller is going to anticipate what's going to happen, it is good, right? So because we are able to correct faster, okay? But that's why the derivative controller transfer function is improper as a standalone transfer function. Once again, we will typically, the way it works out is that the open loop transfer function and the closed loop transfer function will become proper, okay? So that all our design tools will apply. So, but then this advantage of derivative control. However, what are limitations? Okay, so there are multiple limitations. Just as a hypothetical limitation, what do you think will happen if we have a constant error signal? Let us say we want, but however, we have the actual temperature always at 26 degrees Celsius, right? So there is a constant error of 1 degree Celsius. So what do you think the derivative controller will do?
It will keep adding, sir, because it is constant. So as the time progresses, the area under curve will increase.
Area is integral control. Now we are talking about derivative control, right? So let's say the error is constant.
Yeah, it will 0, so it will not give any control because it is the derivative will be 0.
Yeah, exactly.
D upon dt. Sorry.
Yeah, please go ahead.
dt upon dt will be 0 actually.
Exactly, right? So if the error were constant, let's say we have a hypothetical scenario where the error is constant with respect to time, when you and I take the derivative, the derivative becomes 0. As a result, although there is a non-zero error, there is no control action because u of t becomes 0. Okay, so that is the one of the issues with derivative controller. And another important issue is that derivative control can amplify low magnitude, high frequency noise. Because in practice, typically when we measure signals, right, using sensors, we are never going to get a perfect signal, right? Are we? Right? So we are always going to have some noise associated with the sensor. So for the sake of argument, let's say understanding, let's say we plot E of t versus t, and there is a baseline error signal, which is a sinusoidal signal. And just for understanding, okay? So let's say that is sine t. So sine t is our nominal error signal. Now, on top of it, let's say we have some low magnitude but high frequency noise, okay, which comes from sensors. So let's say we call that as 10 power minus t sine 100t. Okay, very much possible, right? So 10 power minus 2 means it's low magnitude. Sine 100t means the frequency is very high, right? So let us say we have such a signal overlapping the base signal. When we take the derivative, what happens is that sine t becomes cos t, and 10 power minus 100 because derivative of sine 100t is going to be 100 times cos 100t, right? And 10 power minus 2 and 100 will result in 1. Now you and I have a problem. What happens is the following. See, what should have been the nominal derivative? It should have been cos t, right? That is, let's say we were in a world where there is no error, no noise in the signal. Okay, so it would be something like this. However, what has happened? Because of derivative action, we are having cos 100t acting on it. So cos 100t also will go between -1 and +1. But what can we say about the frequency of cos 100t? It will be 100 times faster than cos t, right? So we will be getting something like this, right? So it will completely mask the original signal. And this is also a problem. Why? Because we have we would demand a very fast control input, right? Which may not be possible at all, right? By an actuator, because an actuator may have a bandwidth till which it can provide a time varying or a sinusoidal signal. But if the demanded control input exceeds the bandwidth, it would not be able to respond, right? So then we will have issues, right? So this is an issue, okay, with essentially derivative controller, and that's why it is realized in a different way, right? As exercise, I want you to look up at MATLAB, Simulink, or even online tools, and then figure out by tomorrow's class what is the actual transfer function of implementation of the derivative controller, right? So the theoretical transfer function is KDS, but please look at some, let's say, online resources or even MATLAB, Simulink, and so on. And when you search for the transfer function of the derivative controller for implementation, it will be slightly different. Okay, so please figure what that is, and we'll also later learn why it is done the way it is. Okay, but the reason is this. Okay, because if you use derivative controller as KDS, there's a problem because it is going to amplify low magnitude, high frequency noise, which can completely throw the control action out of track. Okay, so that's something which you and I want to prevent. Okay, yeah, or at least minimize. Right. Okay. So now, having looked at P, I, and D, okay, the three blocks, we can have combinations also. So we can have a combination of P and I, which means that we add the transfer function of P, which is Kp, and I, which is Ki. The resultant transfer function becomes Kps plus Ki. Immediately, we can observe that there is an open loop 0 at minus Ka by Kp, open loop pole at the origin, right? So this, by now we know how this comes about. Then we can add P and D, okay? Then in this case, the proportional component gives the transfer function Kp, the derivative component gives the transfer function Kds. So immediately we can see that we have an open loop 0 at minus Kp by Kd. Okay, so that's what happens with PD control. Okay, Then we can have the generic controller PID, where we add P, we add I, and then we add D. Then if we take the LCM, we can see that the numerator polynomial is now a second order polynomial. That means there are two open loop zeros which are added, which are introduced, and then there is one open loop pole which is introduced to the origin. So of course, one may ask the question, hey, what about ID control, right? Because that could also be a combination. Even I and D are not used alone, because due to their action, they are always combined with the P controller, because the P controller sort of, helps, how do I put it, sort of compensate for any aggressive behavior by the I and the D controller, okay? So by and large, as a rule of thumb, in practical problems, we start with the proportional controller. If it works out, well and good, we stop that, because any solution should be as simple as possible, right? But not simpler. So then if P works, well and good. If P doesn't work, we try PI and PD. Okay, so that is the next thing. If something works, well and good. If not, we try PID. Okay, so that is typically the flow. Okay, as far as control design is concerned, right? This is from practice. Okay. So that is the PID controller in general. So we can immediately observe that PI and D have one controller parameter. Okay. So if we start with the P controller, it has only KP. Okay. PI and PD, they have two controller parameters. So in PI, we have KP and KI. In PD, we have KP and KD. In PID, we have three controller parameters. So here we have KP, KI, and KD. Okay, so all the three parameters come into play. Okay, so of course, as the structure of the controller becomes more complex, we have more parameters, right? So the overall control design problem. So please remember where we started off with, right? We had P of S, H of S, and C of S, right? P of S and H of S were known. We want to design C of S. So now if you fix PID control, the structure of the controller is fixed. Now the question becomes, how do we determine the value of the controller parameters, KP, KI, KD, which would achieve closed loop stability and closed loop performance. Okay, so that is the overall task of control design. So you can see how we have progressively sort of like fine-tune the problem. Okay, so the overall problem of control design is that, like, by and large, you and I will fix the structure of the controller. And once the structure of the controller is fixed, we will essentially, go ahead and, choose the controller parameters, right, that appear in the controller transfer function that will achieve the stability and performance of the closed loop system. But that's easier said than done. Why not? Of course, there's always a challenge, right? That's why we are studying this course. So let's say we go for brake control or steering control or suspension control, and we design PID controllers for that, right? Or even like some actuator, electro-hydraulic actuator in a vehicle and so on, right? So the point is, like, even if we start with a proportional controller, right, we have one parameter, right? One controller parameter or controller gain. Now, that is a real number. So if we have KP, it can vary from minus infinity to plus infinity. The question is, what value do we choose? Suppose if you and I have a vehicle, we want to control I'm just taking a simple, right? And we use a proportional controller, right? So, and then you and I need to program the microcontroller, and then we need to plug in the value of KP. So without any design, following any design process, you and I know that KP is a real parameter. So consequently, KP can go from minus infinity to plus infinity. Okay, so that's what one can immediately look at, right? But then the issue is, what value of Kp do we choose now, right? Because if it goes from minus infinity to plus infinity, that's an infinite range, right? So let's say I may want to choose 1 million, right? You may want to choose minus 1 billion, right? Or somebody one may want to choose 0.1. Someone may want to choose minus 20. Right? The question is, as indicated in the above schematic, let's say we finally decide that, look, like if we narrow down this range of Kp from minus infinity to plus infinity to, let's say, a region which is 5 to 30, then what advantage we get is that, like, you and I may be able to fine tune in practice in this range. So imagine going to an actual vehicle and then figuring out, oh, what value do I type between minus infinity to plus infinity? If someone can do an analysis and tell us that, look, you go to the vehicle, but you just try to tune between 5 and 30. That's a huge, advantage, right? And that's what we are going to learn in this course, right? So we are going to learn how do we get these ranges of controller parameters that will give us closed loop stability and closed loop performance. And consequently, right, we will be able to fine tune it, right? When we go to the actual system, right? And we fine tune it in the range that we determine from the analysis. Okay, so that is the overall purpose of this the tools that you and I will learn in this course. So in general, this is what is called as a controller parameter space. Okay, so what is a controller parameter space? It is a graphical visualization of this controller parameter, right? And figuring out what range will give us stability and performance and so on, right? So if we have only one controller parameter, like in a proportional control, the controller parameter space is a straight line. Okay, so suppose if we have PI or PD, right? Then we have two controller parameters. So we'll have KP and KI for a PI controller. Then we have KP and KD for the PD controller. Okay, this is for the PD controller, this is for the PI controller. So then it becomes a plane, right? A two-dimensional plane. So in the case of a PID controller, the controller parameter space becomes a 3D, I think of three-dimensional, right, space. So because we have one axis for KP, another for KI, another for KD, because we have three parameters, right, in a PID controller. So the controller parameter space becomes three-dimensional, right? So now we can immediately observe the complexity of the problem, right? See, at first glance, one may have thought, hey, look, like the structure of C office is fixed, right? We have a PID controller and you and I need to only choose at the most three numbers. Now, let's say somebody is doing PID control, right? It's a infinite three-dimensional space. And ultimately, you and I need to choose a point, because we need to choose a particular value of Kp, Ka, and Kd, which is a point in this three-dimensional space. Now, I hope we can realize the enormity of the task, right, before us, because we need to choose one point in a three-dimensional space to work with a practical system, right? So I hope, the significance of the tools, design tools that you and I will learn through this course become motivated through this discussion. Okay, so what we will continue doing is that, like, as we continue over the next several lectures, you and I will learn how do we design the controllers so that we figure out like the ranges of these controller parameters that will give us closed loop stability and closed loop performance. Okay, so this is what we would have studied in today's lecture. So now open to questions and discussions, please.
Sir, am I audible?
Yes, please.
Sir, a couple of questions. Maybe I'll go one by one. Can you go to the point where you had written that derivative control is actually anticipatory in nature? Yes. from the graph, E of t is plotted as a varying signal which is going to have a downward slope as well as an upward slope. So for that reason, we are saying it can be predicted whether it is going this direction or that direction. That is why it is anticipatory. But the graph which was plotted for E of t, when it comes to integral controller also, there is a chance that it can be predicted, right? Why that is not an anticipatory nature?
Okay. So in integral control, right? Let me redraw the graph here. Okay. So let's say if we have E of t versus t, of course, one can, let's say we are at this time t, right? You can take the slope and you can predict the future, provided you have a derivative term. That's all there is to it, right? So what we did was that like we looked at each term one by one. That is, in other words, if we just had integral control, you and I are only going to look at this area, right? Is it not? Because it's going to look at the historical evolution of error. Now, let us say in addition to that, if we calculated the derivative, you and I will also look at the slope and that will bring in anticipatory nature. Okay, so of course, it depends on what control plot we choose. I hope that clarifies, right? So,
Got it.
see, yeah, these are only pictorial representations so that you and I can get an intuitive feel. So people talk about, say that, oh, integral control captures history, right? While derivative control looks at the future. I just wanted to point out why that is the case, right? I hope that clarifies the question.
Got it, sir. Got it.
Yeah.
Two very basic questions. In dynamics, basically, where will we actually see proportionality between systems?
I didn't get the question completely, Satish. Can you repeat that?
We have proportional controller, integral controller, and derivative controller, right, sir?
Yeah, exactly.
Input signal is always going to be, I mean, if we take omega n or omega d for that matter, it is going to be cos omega t plus I sin omega t or its derived equation. In that case, where do we see the need for proportional controller, or where could we see the application of it?
So the point is the following. See, there are two things. Let me interpret your question in a certain way. Okay. So even I go back to the notion of dynamic systems, right? Let's say if we have a dynamic system as an entity to which we give an input u of t and we get an output y of t, when we talk about the relationship between u and y, okay? So what I could understand from the example that you gave is that u and y could be nonlinear functions of time, right? Cos omega t and so on. Okay, that's okay. But the question is, what is the relationship between y and u, right? Is that a proportional relationship? Okay, then like we have a proportional action. All right. So similarly, if you take this dynamic system controller as dynamic system, you have E of t as input and U of t as the output. E of t and U of t can be nonlinear functions of them, right? But the relationship between U of t and E of t is proportional, and that's a very simple structure to work with. And experience of multiple applications, the proportional controller is practically very useful. That's what we are saying, right?
Yeah, fine.
Yeah, I hope that clarifies your question, right?
Yeah, sir. Just one more question. I'm sorry to keep prolonging.
Please go ahead.
There was one statement on low magnitude, high frequency noise. I just want to understand in practice where will this kind of noise come?
So you take any sensor measurement, okay? So let us say you want to measure some variable, let's say speed of a motor, right? Or a steering angle, right? Or your velocity, or longitudinal acceleration. You will never see a smooth signal, right? You are going to have noise coming into play. That's what I meant. Okay, so but the point
source can be whatever. I mean, it can be anything. Right?
Yeah, the source is stochastic, right? So yeah, exactly, right? You and I do not have control over it. That's why we call noise, right? Because it is unintended, but it's there, right? So we need to address that. Correct? Is it not? So Okay, it can be low magnitude, high magnitude, mid magnitude. Okay, but then what I want to show is that if you have even low magnitude noise, and if the frequency of the noise signals is higher than the base signal, we are going to have issues with derivative controller. That is the point I wanted to drive home. Okay, so despite the fact that the noise is low magnitude, its impact can be quite severe. Okay, so yeah.
That's clear, sir. Just wanted to understand some example on a low magnitude, high frequency noise.
So let's say you want to measure RPM of a motor, right? So even if it's rotating, like at a constant speed, or you brake, you accelerate, and so on, right? Let's say to get a nice wavy signal, right? You will see that on top of that, you will have all these small spikes and troughs, right? Because that is due to the noise. Let's say if there is some misalignment between the sensor and the rotor also, right? Then that also creates problems, right? So all these are practical examples. So when you essentially measure things in practice, you will see that these things come into play, right? And then we need to address them. Okay, yeah.
Thank you, sir. That's from my side.
Okay, thank you. Right, any other questions? No. Think
Sir,
any other questions?
sir, we could, in principle, we can even use ID as a controller, right? So you try to elaborate on that. Why
Please.
that is not coming out to be a practical case?
So typically, once again, we will get this intuitive thing, Satish. Like when you and I design controller, right? 3 blocks, right? You can have various combinations, theoretically, no doubt about it, right? But by and large, one doesn't use I and D and ID, because what happens is that I may lead to actuator saturation, right? D leads to these spikes in the input, right? If the error changes quite fast. Okay. So what happens is that we want the advantages of I and D, but we also want a quote unquote a nice nominal control input which a actuator can provide. Let's think through. Let's say we voltage.
Sir, voice is muffled.
Is it better now? Hello?
Yes, sir.
Hello. Yeah. So let us say we consider the example of a motor, Satish. You and I want to control the speed and we want to give some voltage, right? Let's say if we use I and D, we may end up giving very high voltages or very fast practice. But however, if you use proportional control, the control input is going to be, but not at a rates which are intractable, right, in practice. So what we do is that we combine proportional and integral or proportional and derivatives so that there is a sort of a balance and trade-off between the nice features of the two blocks. Okay, and the controller remains tractable in practice. What do I mean by tractable? The control signals should be physically realizable, right? See, if you and I do some theoretical analysis and generate some control input, the question becomes we need to realize it in practice, right, in a physical system, right? So that's why PI, PD are preferred, right, rather than ID. Okay, yeah.
Sir, maybe, sir, if I want to interpret, let's assume simple equation y equal to mx plus c or y equal to mx. The m portion is what is being done by P controller, and derivative will do dy by dt or dy by dx, some derivative portion with respect to the signal.
Yeah.
And interpret is going to integrate that signal with respect to a variable.
Correct. So if I write the expression for u of t in PID, this is what is going to be, right? It is going to combine all the 3 blocks. That's what you are talking about, right? Is it not?
Yes.
So the point is, if you just use I and D, we are going to have these two blocks, right? So
Yeah.
the risk that the control signal may become too high and it may vary very fast due to derivative action, which may go beyond the capacity of an actuator, right? So that's why what we do is that we do this or do this and this, right? If needed. So that sort of like the proportional controller sorts of balances the limitations of IND, while we have the advantages of IND also coming into play, right? So, like any other design problem, Satish, we should have the simplest possible solution, right? See, if you generally ask, I would always say, hey, use PID, right? But all the three blocks may not be needed for all the applications, right? That is the point. Okay, yeah.
Thank you, sir.
And when we start doing problems and examples, I'm sure we will realize it. Okay, so as I told, theoretically ID is possible, but in practice, from a practitioner's perspective, we don't use it. Okay, that is the point. All right. Any other questions?
Am I audible?
Yes, yes, please.
Prem here. So this KD value or any constant that we are multiplying as a controller, those three parameters,
Yes.
typically that will get affected by the actuator or the end system alone. I mean, which we are trying to control.
That will also play a role. Okay, so the plant dynamics will play a role. Okay, the actuator capacity may play a role. Okay, and there may be other constraints coming in due to stability and performance considerations. So we are going to look at all those things, right, as we go on.
Okay, the reason why I asked was since it's belonging to a subset of R, so whether it is constrained by something and then we can reduce a set. That's the reason why.
Yeah. So what we are going to do is that, like, see, even if we take KP, right? So it's a real line. Okay. So as we understood, the value can be anything between minus infinity to plus infinity. Like even what I called as the simplest controller, the design process is not very simple and straightforward, right? Because what value do we choose between minus infinity to plus infinity, right? As we discussed, you may like 1 billion, right? I may like minus 10 million, right? So what value do we figure out, right? So we have to look at all the practical considerations and do the design. Okay.
Noted, sir.
So is that mean that the value of KP is like limited by the actuator capacity?
It is only one of the constraints, Roshan. Okay, not the only one, right? So, yeah.
Okay, sir.
Okay, so first you and I will look at like closed loop stability and performance, and when you fine tune it, like see the actuator constraint, you will be able to see when you do simulations. Let us say you use an actuator with a bandwidth of 1 Hertz, right? That means the fastest sinusoidal signal it can provide is a sinusoidal wave of 1 Hertz temporal frequency, right? Let us say you design a controller, Roshan, and then in simulation, you figure out that, oh, okay, I need a control input which has a, oscillatory temporal frequency of 10 Hertz. Then that value of KP is not tenable, right? Is it not?
Right, sir.
Because you don't have an actuator for that. That's what I meant. Okay.
So basically, I was imagining that suppose I have a 1000cc engine or maybe 1.5 liter engine, and I want to drive a truck with that engine probably.
Yes.
So that suppose I have a transmission.
Mm-hmm.
So if I assume that to be a actuator, for what I want to say is not actuator, for a multiplier of torque in that sense. So whether I can increase the ratio of the transmission in such a way that even with the low torque of the engine, can I drive the truck or not? So what problem is actually I will face in that sense that I will trying to imagine.
Understood. Like, so see, of course, but one needs to understand that we need to pose it as a control problem. See, I think that is the main point I would share, Roshan, because you and I need to pose it as a control problem before we can, solve it, right? So, see, you remember the class of systems that you and I are studying, right? Linear time invariant, causal dynamic system, and so on, right? So the question becomes, can you and I pose it in that way, and then like go ahead and solve it, right? So that will determine, right? So how far we can apply the methods that you and I are learning in this particular course. Okay, so that's important. So even in your problem, the important step is to formulate the problem such that it is done, it fits the theory that you and I are trying to apply. Okay, so that's what. Okay.
Right, sir. Thank you, sir.
Oh, okay, so it's already 5:52, right? So Arunachal, is everyone present today? No, sorry.
Sir, only one absent, sir. Valish.
Who's absent? No.
Valish R, sir.
Valish. Okay. Yeah, Valish. Yeah, okay. Everyone else is present. Is it?
Yes, sir. Yes.
All right. Okay. So I think, yeah, so it's almost 5:53, right? So I think we'll stop here today. We will continue with our discussion tomorrow, right, on the next video, and then we'll proceed in this course. Okay, so yeah, you can continue to ask questions tomorrow also. Okay, so on today's content. So we will meet tomorrow at 5 p.m. Thank you, everyone.
Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.